my name is Mariano Zeron, and in this video I'm going to show you how to build and evaluate MoCaX objects of dimension greater than 1. So what is the situation that we're involved with here? So we already know what the problem is with one-dimensional functions and how to build the corresponding MoCaX objects to approximate them and how to evaluate these objects. We'll see that all the notions that you've learned for one-dimensional functions readily extend to higher dimensions. But in this case, instead of one dimension, let's say we've got a two-dimensional function. Partly, I've chosen 2 dimensions because it's easy to visualize, but also you'll see that everything that applies to 2 dimensions equally applies to all other dimensions. So say that we've got a 2-dimensional function here. So let's say this is the y-axis, this is the x-axis, this is our z-axis. So you've got a surface up here. This is the function that you want to approximate. So the first thing that we need to do is define a domain of approximation. So the domain of approximation is going to be a rectangle on the xy plane. So I'm going to draw it here for perspective. But if we saw it from above, what you have is, let's say this is the x-axis, this is the y-axis. What you have is basically an interval on this line, say between a comma b, or a and b, and then another interval on the y-axis between c and d, and that will define a rectangle, which is going to be our domain where we want to approximate the function. So that rectangle is the one that you've got here. And that is the first thing that we need to define in order to be able to build a MoCaX object for this particular function. The second thing is going to be the definition of the Chebyshev mesh on this domain. So how do we define a Chebyshev mesh in dimension 2? And the way that we do it in dimension 2, you'll see that you'll be able to extend it to any other dimension. So we know how to define Chebyshev points on one dimension. So you can do it for this interval here. So you've got these points here. And you can also do it for this interval over here, CD, because that's one-dimensional as well. So we define them there. Take the Cartesian product, that's going to give you a collection of 2-dimensional points, which are going to be contained within this rectangle, and those are the Chebyshev points for that rectangle. So we end up with points here, 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 and the corresponding ones over here and over here. So those are going to be the Chebyshev points that we're interested in. So that is the second bit, or the second part, which is essential to the building of a MoCaX object. And the final third part, which we need, are the values of the function f, which we have here, on the Chebyshev point. So those points here correspond to, let's say, points over here in this domain, that when evaluated under the function correspond to values up here, say. And we'll need those values to finally have an object that you can evaluate and use instead of the function f in whatever risk calculation you want. So let's take a look at some of the code that I've prepared for you, where we will see this in detail. We'll see the scripting of it. So we've chosen our function to approximate to be Black-Scholes 2D. Say that, so we know that it's a 2-dimensional function. So the first parameter that we need to specify is the number of dimensions, which is 2. The next thing that we need to specify, as we saw here, is the domain of approximation. So how do we specify that? The information of the domain is contained in an object of type MoCaX domain, which is the thing that I've highlighted there on the screen. Now, to obtain an object of that type, we need to pass to the class of MoCaX domain, to the initializer of MoCaX domain, we need to pass a list of intervals. So the list of intervals is this one up here, that has, as you can see, in its first entry, an interval between 50 and 150, which is the interval that would correspond to a comma b here. In particular, in our example, that variable is the one that corresponds to the spot. So it makes sense to choose values of, let's say, between 50 and 150, partly because I've chosen the strike of the Black-Scholes function to be 100. The second interval that you specify, which is this one here, c comma d, corresponds to volatility. So I've chosen these other values here, 0.2 to 0.4. If the function was of 3 dimensions, then we would need to add another interval there, and you would put values whichever you thought were appropriate, 1.3 to 1.9. This is just an example. And if it was 4-dimensional, you carry on adding intervals. So that's it. That's all you need in order to specify the domain. So that's one of the bits we need for the construction. The second that I mentioned were the Chebyshev points within that domain. And I said that the way to come up with Chebyshev points is by specifying Chebyshev points in 1 dimension. First of all, on the interval of the first variable, then on the interval of the second variable. If you have 3 dimensions, you would need another integer to specify the Chebyshev points on the 3rd dimension. So what you need to have, as you see on the code, is a list of integers. In this case, is a list with 2 integers. In this case, 4 and 10. The 10 corresponds to the number of Chebyshev points that you want in the 1st dimension, and 4 corresponds to the number of Chebyshev points that you want in the 2nd dimension. If you had a 3rd dimension, you would need to add another integer, let's say 5, for example, and so on. That list of integers is then passed to the constructor of a type called MoCaX NS, which is the class that defines or carries all the information of the MoCaX points. So once you've built that, we've got this variable called NS that we'll also need to pass to the initializer of the MoCaX class, which we see down here. So this is essentially all the information, or apart from the values of the function on the Chebyshev points, that's all the information that you need in order to build a MoCaX object. But I also want to show you how to build special points, which is not needed to build the objects, but this allows us to come up with splines of Chebyshev and so on, which is something that I explained in a different video. I suggest that you, if not familiar with what special points does in a Chebyshev object or in a MoCaX object, I suggest that you take a look at that video. But here, the only thing that I want to make clear is the way to build an object of type MoCaX special points, which is the one that carries all the information of special points in higher dimensions. And the way that we do it is by considering a list of lists. So this is going to be very important. The list is going to contain, in its first entry, all the special points of the first variable. So let's say that you've got, again, let's take a copy of that, of the domain. So here's A, this is B, C, and D, and this is our domain, square, or it's the rectangle. This is our first dimension, that's our second dimension. We want to introduce a special point. We know that it has to be in between A and B. So you can specify as many special points as you want. They can be here, 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 and here, for example. That has to be put into a list. Then you go to the second dimension. How many special points do you want? 1? That. Put it into a list. You don't want any. It's fine. Don't put any. But still put it into a list which is empty, which is what you can see in the code. So here, this list of lists, I've called it spec points. The first list contains 60 and 80, which is within my domain of the first variable, which is 50 and 150. And the second one is empty because I just happen not to need special points in the second dimension. If we had a third variable or a third dimension, I would need to add another list there, which could have some special point, but if you don't want to specify any special points, leave it empty. But it's important that you have them there. Okay, so that takes care of special points. By the way, this list, of course, would need to be passed to the initializer of MoCaX special points, and the object that it returns is the object that then you can pass to the constructor. And the last parameter that I want to talk about, which is again not needed to build the object, is an extra functionality that the library provides, is the derivative order to which you want to build your MoCaX object. I've explained what the derivative order does in another video. I suggest that you take a look at it in case you don't know what it is. But for the time being, the only thing that we need to know is that it has to be a positive integer. It just specifies the degree of the derivatives that you want to be able to approximate with a MoCaX object. That is it. But once we've specified all these parameters, what we have is the possibility of building an object, with the exception that we're still missing the values of the function on the Chebyshev points, and I'll go into that in a second. But what I want you to see is, assuming that we can run this script, which basically takes care of the construction of the object, I want you to see how it looks in 2 dimensions, how we can control the accuracy of the MoCaX object in 2 dimensions. So let's say that we've got the function that I want to approximate up here, which is, as I said, Black-Scholes in 2 dimensions. I've wrapped what you just saw in the previous script into a couple of functions so that they don't create a lot of noise on the screen with so many lines of code. So the domain here, I've specified it just as a list where I go and I put A, B, C, and D, where A is this, B that, C, and D is that. So basically that specifies the rectangle where you want to approximate the function. So that's the domain. Now, I've got the ends, which are the values that specify the number of Chebyshev points in each of the dimensions. So the first n, which there is 13, is the one that gives you the number of Chebyshev points here. The second one gives you the number here. And those are the only 2 parameters really that you need in order to be able to run this script. Because once I run it, which essentially means I want to be able to build the object, so we run that. We also print it. We see the description here on the right-hand side. It tells you everything about the object that you need to know, the one that you have. Then we evaluate it, which I'll tell you in a second how to do. Don't worry. Boom. And then finally, what I want to show you is how it compares to the original function. And what you see here is a plot of the surface of Black-Scholes. And on the right-hand side, which is probably the most important part, is that you see the accuracy that you have. And the accuracy here, because I've printed it, the max error, is of 10 to the minus 5. And this is with a mesh, or the size of a Chebyshev grid, of 13 times 7, which is not much. And you can start playing around with the values of n to see how you can control the accuracy. Let's lower them so that we get a bad level of accuracy. Let's say 5,3, and run the whole thing. What do we get? On the right-hand side, you see that you get an error of 2 times, well, is of the order of 10 to the minus 1. It's not, to be honest, it's not bad at all. But if that is basically our starting point because the mesh is tiny, you can, by slightly increasing it, so let's say 7,4, you're already on a level of accuracy of 10 to the minus 2. You need more for whatever reason, increase it slightly. This is where you can see the power of exponential convergence and the approximation of Chebyshev polynomials and spectral decomposition and so on. It's just by slightly increasing the size of the mesh, which in this diagram it would translate basically into seeing more of these points here. That's all you do, basically. And of course, sampling the function on those corresponding points, but that is it. If you increase that slightly, again, 10 to the minus 4, and so on and so on and so on. You can start playing around with these parameters and start seeing what the level of error is. So let's go back to finish off the description of how we build a MoCaX object in this case. So the bit that we had covered basically showed we need specify the dimension. Well, that comes with a function that you want to approximate. Trivial. You want to specify the domain. Fine. Give me the A, give me the B, give me the C, give me the D. Put it in the right format, which is a list of intervals. Feed it into the initializer of MoCaX domain. You've got your domain. Third, Chebyshev mesh. How do you control that? Well, it's going to be a list of integers. How many integers? As many as the dimensionality of the function. Done. You feed it into the initializer of MoCaX NS, and you've got the object that then you can pass to the MoCaX initializer. And of course, you're interested in introducing special points, you can do it as I mentioned. You want the derivatives, specify derivative order with a positive integer. Done. Now, what is missing? The values of the function f on the Chebyshev points. So what you do is the same as we did with the one-dimensional case, for those who have seen that video, is there is a function here, a method of the object called get evaluation points. That returns the anchor points. So basically, you then have access to these points. You can actually see them. You'll be able to get them. You'll be able to then send it to whoever has the function you want to approximate so that they evaluate those points. They'll give them back to you. Those values are denoted here by vals anchor, and those you have to feed into the object using a method called set original function values. And if you do that, then your object is ready to be evaluated. So let's run this, because you see, as I mentioned in the other video where I covered the main functionalities, print is a function from Python that can be used with our library. So you can print the object and see the description of it. I've printed it here when we did the first stage of the building process, and you get unfinished construction. So far, you would not be able to use the object to be evaluated. Then you finalize the construction, which is when you feed in the values of the function on the Chebyshev points, and that gives you an object that when you print, no longer shows unfinished construction and gives you all the details that you need from the object in case you want to inspect it and so on. So how do you evaluate this object? And it's essentially the same as we did with one dimension. So here in this file, in this script, the first part is just a wrapping of what I showed you before. So it's basically just to build the object. We've got the objects already there loaded in memory. And the line that is important to pay attention to is this one that I'm going to highlight, where you take MoCaX object and you call its method eval. Now, eval takes two parameters: point, which is the point that you want to evaluate, and derivative ID. Derivative ID for the time being, don't worry about it, is just the specification of which order derivative you want to evaluate. But if you don't specify it, it's fine. It comes with a default value of 0, which means just evaluate the original function, or the replica of the original function. But the important one is point. And point is just essentially a point in your domain that you want to evaluate, which has to be, of course, within the domain, because if you put it out here, the library will raise an exception and you'll see it. It'll print out wrong. You can't evaluate something which is outside the domain. So it has to be in here. What I've done in the code is come up with a mesh of points. Let's say all these points. So a collection that covers all the domain, basically. And I want to evaluate them all. This is similar to what you would do in a risk calculation. You have a collection of points that you want to evaluate. So essentially here, what I did is just come up with a grid of points within the domain. And what I want is the value of the replica of f, not of f, of the replica, the MoCaX object on those points. So what you need to do if you've got the collection of points is go one by one and feed them to the eval method, and that will return the corresponding value of the object. It's as simple as that. And this is basically what I have in this bit of code here. And really, the last thing that I described with the going point by point is just this. The bit at the top that I've highlighted, this is just getting ready the collection of points that you want to evaluate. That's it. So you can wrap this into your own method, your own function, whichever way you want. This can be, of course, part of the functionality that you implement in your own class to put it within the rest of the code that you have in your engine or your own system or whatever it is. So as you see, it's very easy to get hold of the main functionalities of the library that we provide, and you can include it very easily within your own collection of classes, functions, and so on. And so this code can then be wrapped to finally obtain what I showed you at the beginning, which is the specification of a function that you're interested in, specification of important parameters, which really it's only two, the domain and the Chebyshev points within the domain, build the object, which is this, finished, great, evaluated, use the values. In this case, we're comparing to the original function, super accuracy, which we see down here, bam, 10 to the minus 4 with a pretty small mesh. So great. So there's one more thing that I want to show you. If you notice, when we build the MoCaX object, we built it up with derivative order equal to 2, meaning that the object is capable of replicating not only the original function, but also all the derivatives up to order 2. So let's take a look at a code that I prepared for you so that you see exactly how it performs in terms of accuracy when it wants to approximate these derivative functions. So what do we have here? So over here, we've defined the functions that we're going to be using. So we have the first one is the Black-Scholes function, which is going to be used to build the MoCaX objects. The remaining ones, which are the delta, gamma, vega, vanna, and vomma, which are all the derivatives up to order 2, they're only going to be used for benchmarking. That is, in order to compute the error that we make with respect to between the MoCaX object and the function that is trying to replicate. So let's see what happens when we build the object. We've specified derivative order equal to 2. So this bit that I'm highlighting is to build the object, as you had seen before. So let's run that again to cover the imports. So that's the object built. Then let's create the mesh over which we're going to be evaluating the degree of accuracy. And let's run the first MoCaX object, which is, let's run the MoCaX object specifying that the derivative that we're interested in is that which corresponds to the original function, which is specified with 0, 0. So basically, we're telling it, don't go for any proper derivative. If we do that, we evaluate the MoCaX object, which is what I've highlighted, and then the last line is the plotting of the surface and the plot of the error that you're going to see on the right-hand side over here. This is the surface, corresponds to the Black-Scholes function, and over here is the error, the relative error, but the maximum. So it's basically as how bad it can be. And in this case is the order of 10 to the minus 5. So it's basically what we had seen before, but now we're going to see the actual derivatives. So if you want to see what happens with delta, in order to evaluate with the MoCaX object the replica of delta, we have to specify the derivative in this particular way, which is 1, 0. We run it, plot it, and what do we get? We get the delta, as you see here on the right-hand side, along with its corresponding error. And we have 10 to the minus 4. We do the same with the remaining derivative. So first of all, the first order derivative with respect to the other variable, which is vega. So we get the surface of vega along with the error, 10 to the minus 3, gamma, and then we're going to get vomma, which is the second order derivative with respect to the second variable, and then the cross derivative, that is vanna, which is derivative with respect to one of the variables followed by the derivative with respect to the other variable. We plot it, and we obtain, in this particular case, a relative error of 10 to the minus 3. Notice that the mesh that I'm using is still pretty small. It's only 15 times 5. So if you want to improve the degree of accuracy for any of these plots, just increase it slightly to, say, 20 times 7, and you'll get an extra order of magnitude. Bear in mind that the rate at which the MoCaX object approximates any of these functions is very, very strong, is exponential. So that's why you don't need to increase the mesh by that much. So in this video, what we saw is basically how to build MoCaX objects for functions that we want to approximate, which have dimension greater than 1. We had seen in previous videos how to do it for dimension 1. Now we saw it for dimension greater than 1. So what you saw, even though I stuck to 2-dimensional functions for illustration purposes, can be extended, or it's basically you do the same thing if you want to cover 3-dimension, dimension equals to 3, 4, 5, and so on. If you've got any queries, please get in contact with us on the email that you see on the screen, and see you next time.